m and n. Then we have linear operators from m to n. Then we have bounded linear operators from m to n. These are also continuous ones. Okay. If you take T in bounded linear operators, there are several equivalent constraints. So one of them is that supremum over mod x norm x less than or equal to 1 of norm tx is actually equal to supremum over the surface. This is the whole ball. This is the surface of the unit sphere of norm tx. These two are same. Okay. If it is bounded linear. If this is true, then it is bounded linear. Okay. So suppose you call this as say some A and this as B. If A is finite, then T is continuous. Because all these conditions are, we have shown it to be equivalent. So to show continuity, this is a very easy method of doing it. Nothing like an example, right? So let's take an example. Let's take a map. S from L1 to L1. So what is this L1? L1 is nothing but a sequence xi such that summation I equal to 1 to infinity mod xi is finite. What is this map? This map you define it as shift. Okay. So let me shift it to the left. Last time I had told you right shift. Okay. I'll shift it to the left. That means it is x2, x3, etc., etc., xn dot dot. Okay. You are shifting it to the left. Therefore, that x1 will disappear. Okay. Now, want to give you the fact that this is a continuous map. I don't know what has happened. This mouse is not working. Yeah. Okay. We want to show whether it is continuous or not. Okay. So let us take norm x, say equal to 1, and look at the norm of Sx. This will be the norm of the point x2, x3, xn, right? Because that x1 goes out. This is how you define Sx. This will be less than or equal to norm of x in L1. Why? Because this norm of this is summation from I equal to 2 to infinity, mod xi. And therefore, this is smaller than or equal to, you add a mod x1 to it, therefore this becomes less than this. This is anyway equal to 1 because you use this. So this implies that x is arbitrary with norm x equal to 1. Implies now the supremum is less than or equal to 1. Therefore, this is less than or equal to 1. But we would like to calculate the norm itself. So, the supremum, if it is attained at some point, then we are done with it. So, what you do is, you take the element like 0, 1, 0, 0, 0. Okay. So, let me call it as some p. Actually, this is E2. Norm of E2 is 1. Please understand this argument carefully. Eh? And this S of P will be actually, that 0 drops out, and what you get is this is a shift operator. This implies that norm of SP is 1 and norm P is 1. That means the supremum is attained. It is attained at P. Supremum is attained at P. Therefore, norm of S is, complete. It cannot be bigger than 1, but the supremum is attained at a point. Therefore, norm of S is complete. 1. Yes? Is it clear?
Yes, sir.
Good. So you know how to calculate the norm now, okay? You may get a bound, but you can also calculate. So that is the first thing. Second thing is, recall that this BLMN is complete if N is complete. This I have proved it in the class. Okay. Third thing, it is there in the dancer's book. Third thing is, M star is defined to be BL, instead of N, you have the scalars. This is called the dual of M. Some people call it as a norm dual of M. Okay. So what are these elements? These are linear, continuous functionals from M to C. C is obvious. Okay. C or K. So let F belong to M star. Then you have the null space of F. Some people call it as the Z of F. This is called the null space. So what is this null space of F? Set of all X such that F nullifies it. Fx is 0. Okay. Then this is a closed subspace. It is also called a hyperplane. Okay. Usually hyperplane means one dimension less. Okay. I will add few more pages. What do you mean one dimension less? Huh? One. It simply means or something has happened. ठीक है. Just 1 minute. Huh? Yeah. One dimension less. Okay. One dimension less. See, suppose you have infinity. What do you mean by one less than that? So it doesn't make sense. So what it means is, if you take a functional non-zero, okay, and if you take a point x which is not in the null space of f, then your space M is nothing but the null space of f plus x sum. Okay. If you don't like this, you may write this as a subspace generated by x. So one point outside, if you add it a subspace to this NF, then you get the whole space. F is in M star, linear continuous. This is true. That is why it is called one dimension less. One dimensional less subspaces are called the what is called the okay. So the third thing is Hanmanak theorem. So let you have M to be a nonlinear space, and N is subspace. Let F belong to N star. Functional, okay? Then there exists an extension F bar belonging to M star such that norm of F equal to norm F bar and F bar restricted to M will be F. This is extension. Okay. This is the Hanmanak theorem. So you might ask what is so great about it. It's great because it has too many applications. So one application I'll give you today. Suppose M is a nonlinear space. X, Y is in M and X not equal to Y. Then there exists F in M star such that Fx is not equal to Fy. That means F separates x and y. Okay. How do you do that application? So take z equal to x minus y. It is not 0. Now you look at the manifold generated by z. Okay. Call it as n. Right. You can also have norm f equal to 1. Okay. Now what you do is you define on n. So this is nothing but the set of all alpha z's such that alpha is in scalars. Okay. So you define f of z, so alpha z equal to alpha. This is linear continuous. Therefore, f belongs to n star. Apply Hahn-Banach theorem. What is the norm of this? Okay, what's the norm of this? Hmm? Calculate it. Huh? I will not do it for you. Okay. Then this f has an extension. F has an extension. Call it g. Okay. Then g of z, you know, so g of z is non-zero because alpha is non-zero. And therefore, g is nothing but g of z is x minus y. That is non-zero. Apply the linearity, then you get g of y not equal because this implies this. So this is a very simple application of the Hahn-Banach theorem. All right. Now we come to fifth part. Let M and N be two non-linear spaces on the same scalars. A map T from M to N is called an isomorphism if one T inverse belongs to, I should say T belongs to bounded linear M, T inverse belongs to bounded linear N comma M. That is, T is 1, 1 and not 2. First condition. Second condition, T and T inverse are continuous. Then it is called a linear isomorphism. So what it says is it supports, it respects vector space structure and topology. That it is linear supports the vector space structure. That it is continuous supports the metric topology. Okay. Now, So if okay, if T is M to N is an isomorphism, then we say these are definitions, okay? M and N are isomorphic. So second, so you look at the set of all bounded linear transformation from M to N. So you say that T is equivalent to S if both T and S are isomorphisms. No, sorry. You say that M is equivalent to N if there exists an isomorphism T from M to N. That is, T is continuous, T inverse is continuous. T inverse exists and it is continuous. So, this M equivalent to N is an equivalent relation. What do you mean by that? M is equivalent to M. M equivalent to M if and only if N is equivalent to M. Symmetry. M equivalent to N, N equivalent to some P implies that M is equivalent to P. Okay. Essentially, what we are saying is this the two vector spaces are almost the same. Only thing is we call it in a different name. Okay, example. Let us take say M to be complex numbers with real field, and let us take N equal to R2. Okay. An element here is denoted by X plus Iy. The element here is denoted by Xy. So you take this X plus Iy, so T of X plus Iy, you define it as Xy. Then this T is an isomorphism from M to N. What exactly we mean by that? We write it here as X plus Iy. So इसका नाम है that X plus Iy. But it is written here as a vector P with two coordinates X and Y. You write it as X plus Iy, but it is same thing as Xy. I mean, the way you write here and the way you write in the other space is only the difference, but otherwise there is no difference at all. So you can see here that the uh, the fact that the nomenclature here is X plus Iy here, then the name here is changed to the real part with the imaginary part as an ordered pair. That's all the difference. But there is otherwise there is no great difference. You can also take polynomial of okay, polynomial of say say P1. degree less than or equal to 1. Right? So there are two elements, right? 1 and x. These are the two things that any element here will be a plus bx. You map it to ab. Right? This is in R2. So this map T is an isomorphism from this P1 to R squared. You can verify it's an isomorphism. Here we call it as A plus Bx. Here you call it as A comma B. So only the name is slightly different, but otherwise the rest is the same. But you have to be careful. Properties on one space need not hold on the other space. For example, A plus Bx, you can differentiate. It's a function. Whereas A comma B is not a function. It's an ordered pair. You can't differentiate it. So some properties, essential properties, it may have, but vector space property is specified. If you add two, so for example, you add say A plus B and add C plus dx, then what you get is A plus C plus B plus D into x. You add the two coordinates, A, C, D here, you add here. What you get is A plus C, B plus D. First coordinate you multiply by 1, second coordinate multiply by x, you get this. Nothing else. So the way you add here, the same multiplication, the same addition is carried over. So that means the vector space structure is preserved. Continuity also is preserved. Okay. So all, so I mean, what do we expect now is the following. Okay. All finite dimensional linear spaces. All finite dimensional, same dimension. Linear spaces are isomorphic. So we work with Rn dimension n. Any vector space, any non-linear space of dimension n will be isomorphic to this. So as well we can work in Rn and get back to the isomorphism. Proof is not trivial, huh? Okay. So we will try to prove this theorem today, if possible. I'm not saying I'll be able to prove it. I will try whether I can do it today. Okay. So let us relax for 1 minute. Huh? Any questions? Any doubts? No.
No, sir.
Any questions or any doubts? Is it clear? I have completely recalled what I have done in 3 days, huh? In your place, except that the spaces are. So what is that we expect? We expect all finite dimensional spaces to be isomorphic. See, that is expectation. It is like we think that it might happen. It is like a motivation that we feel they should be like the same. But you need to give a proof. So let us try to look at uh, the proof of that. Okay. Are you able to see it? This is the equivalent terms. I have done it.
Yes, sir.
But let me give you again. I will do the same thing. This is the finite dimensional space. This is what I wanted to do today. What it says is, if E is a finite dimensional vector space, then all norms are equivalent. Moreover, if E is complete with respect to every norm. So all norms are equivalent is as good as saying all the vector spaces are isomorphic. Okay. So let me give this first part and then go to the second part. Okay. What do you mean by two norms are equivalent? 9.1 definition. Suppose that E is a vector space and there is a norm 1 and norm 2 on E. He is talking on the same vector space. He says that norm 1 is stronger than norm 2. Norm 1 is stronger than norm 2 means whatever happens in 1, it will happen in 2. That's what it means. Okay? If there exists a constant C such that norm of x2 is less than or equal to norm x1 for all x in E. The same way, if x1 is stronger than x2, you call x2 weaker than x1. Right? That somebody is stronger than x is stronger than y. What we say is y is weaker than x. Okay, something like that. What you should understand is that if you have a sequence converging with respect to norm 1, then it will also converge with respect to norm 2. That is what the Lemay's proof, Lemay's way of defining the equivalence, which we have done earlier. So these two definitions are equivalent, whatever I had given earlier. We say that the two norms are equivalent. If C norm 1 is equivalent to norm 2, okay, let me be very clear here. Norm 1 is equivalent to norm 2. If there exists constant capital C and small c greater than 0, strictly greater than 0, such that C times norm x1 is less than or equal to C, norm x2 less than or equal to capital C times norm x1. Okay? Please note that norm x1 and norm x2 are equivalent. So this x2, which comes second here, will be in the middle part of it in this inequality. If you say that norm x2 norm x2 and x1 are equivalent, then this 1 and 2 will be interchanged. Be careful, huh? Okay. Now, what is the so you look at the LP norm, P norms on Km. This P can be 1 less than P less than infinity. Then it's a norm. 1 less than or equal to P less than or equal to infinity. There is a question many people have been asking me. Sir, what happens if 0 is less than P less than 1? Then it turns out this, whatever the norm you define through LP, that's not a norm. Do you understand what I'm saying? What is so great about P greater than 1? That's what I'm talking about. I will explain to you what I mean. What I'm saying is that this 1 is less than P less than infinity, less than or equal to. Then this norm, P, is a norm. We have done it. Holders inequality, etc. What if 0 is less than equal to P less than 1? What is this case? This will not define the norm. How do you show that? So in this case, a ball of radius r around, say, ball of radius r around 0 is convex. Whereas in this case, it is not. So if you have an norm, is an norm, then the unit ball is convex. That is simple, okay? So you take xy and you look at z equal to lambda x plus 1 minus lambda y. Look at the norm x, okay? This will be less than or equal to lambda is positive, 0 less than 1. Then this is lambda times, this is 1. plus 1 minus lambda times 1, because this is of norm 1 unit pulse. So this will be, this lambda cancels, what you get is a 1. So that implies that Z is in the unit pulse. That shows that this unit ball is convex. It is true in any nonlinear space. But in 0 less than p less than 1, this is not convex. It's not convex. I have not done this, but you can do it yourself. Simpler way of doing it is draw the graph and then you will see it. Okay. So in one case, the ball looks like something like this. You take a point here and you take a point here, and this line is inside this. Okay. In the case 1 less than p less than, sorry, 0 less than p less than 1, the unit ball will be like this. Draw the graph. Huh? If you take 2 points like this, 1 point here and 1 point here, you draw the graph. This line is not inside unit ball. And therefore, this unit ball is not convex. What is the important point of it? You should know how to draw the graph of this, right? So you should, suppose you take p equal to say half. You should know how to write the ball of radius 1 around 0 with this norm. Okay? Draw it. So it's a question of simple. Rishabh was saying you need geometry. Okay? I'm bringing in geometry. Draw the graph. When you draw the graph here, you will get something like this. And that will not be convex. Since it is not convex, the norm cannot be, the p 0 less than p less than 1 cannot be a norm. If it were to be a norm, then the story is that the unit ball would have been convex. It is not convex and therefore it is not a norm. Okay? So what are the examples here? Let norm xp denote the p norms on kn. We have done this. Kn is only finite sequences. All right. So LP is the infinite sequences. Take 1 less than or equal to p less than or equal to infinity. And you can show that whatever we have earlier shown, that this norm of q less than or equal to norm p is less than or equal to n raised to q minus p over pq into norm q, provided q is greater than p. That is the consequence of Jensen's inequality. Okay? So this tells you that several, this norm xp is stronger than the norm xq if q is greater than p. All right. So these are some remarks. You can read it up yourself. Okay. It is in terms of the metric topology here, what Lemieux's book had given. So these two become the same. Okay. If norm 1 and norm 2 are equivalent norms on E1, then E1 with norm 1 is complete if and only if E2 is complete. That means if we have two norms and they are equivalent, then if one space is complete, then the other space also has to be complete. Then it's a trivial one. Okay. Proof is very, very simple. And then you have something to do with the graph. I will not do that. Okay. All right. Now we come to the finite dimensional linear space. What do you mean by finite dimensional linear space? That it has a basis, Hamel basis with finite number of elements. The number of elements in a Hamel basis is called a dimension. Suppose E is a finite dimensional space, then all norms are equivalent. Moreover, E is complete with respect to every one norm. That is the next theorem. Okay. It may take some time to do it, and therefore, what I will do is I will prove this theorem tomorrow. Okay. Stop sharing. It's about 2-3 minutes to 11:50. So you normally I stop the class about 5 minutes or 10 minutes before. Since I have to start a new theorem, it will be half done if I do it today. So tomorrow's material will be to show that all finite dimension linear spaces are isomorphic, same dimension. And if one space is complete, then every finite dimension space is complete because Rn is complete. Structural proof is that you show that any vector space is of dimension k is linearly isomorphic to one typical example of a finite dimensional space, and we prove the other way around. What is used here is that if you are in Rn, please note, if you are in Rn, then the unit ball, closed unit sphere is compact. And so any continuous function on a compact space attains maximum and minimum. That is the text of the proof. It's simple proof. We will try to do it tomorrow. Okay, have a good day. Enjoy yourself. Bye.
Thank you,
Okay,
sir.
sir. Thank you, sir.